Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Central University of Haryana, Department of Physics. Today we are going to discuss about the module The Theory of Relativity 1 from the paper Electromagnetic Theory. So from this module, what you will really get to know about is the following. 1. Many crises were faced by the physics at the end of the 19th century. The resolution of the problems of light leading to the formulation of the special theory of relativity. Then, you will also learn about the Michelson-Morley experiment and the importance of the null result of this experiment. Then, we will discuss the postulates of the special theory of relativity. We will then go on to discuss the Lorentz transformations of the space-time coordinates as viewed in different moving frames of reference. Then we will discuss the revolutionary and counterintuitive implications of the consequences of the Lorentz transformations of the space-time coordinates, that is, the length contraction and the time dilation. And finally, we will discuss about the relativistic Doppler effect. Now students, the world of physics faced two very special problems in the last quarter of the 19th century. One was theoretical and concerned radiation by black body, and the other was an experimental one and concerned certain velocity of light measurements that were made by Michelson and Morley in 1887 in their famous Michelson-Morley experiment, which was proposed to prove the existence of ether, or rather to test the existence of ether as the medium of propagation of light. The subsequent solving of these two problems led to a double revolution in physics, which changed the face of physics forever. The first problem, the problem of black body radiation, led eventually to the birth of the quantum theory. What concerns us here is the second problem, highlighted by the null result of the certain experiment due to Michelson and Morley in 1887, which was solved by Einstein and led to the special theory of relativity and eventually to the general theory of relativity. After Maxwell wrote down the equations of the electromagnetism, which admitted of wave-like solutions with velocity equaling the velocity of light, the subjects of optics and electromagnetism were truly synthesized. Other waves, such as sound waves and water waves, need a medium for them to be transmitted. They cannot travel through vacuum. It was thus natural to believe that a medium was necessary for transmission of light, that is, the electromagnetic waves as well, because light is an electromagnetic wave. This medium was at that point in time called the ether, the aether, or the luminiferous ether, which filled up all space and vibrated as light waves passed through it. To get the correct value of velocity of light, this medium ether needed to have some peculiar properties: negligible density, high elasticity, and negligible interaction with matter, as if it was created for the sole purpose of providing a medium for propagation of light waves. However peculiar its properties, if it exists, we must be able to perceive the motion of material bodies with respect to it. All attempts to find this relative motion failed completely. Michelson and Morley's experiment was one such experiment, and its negative result proved the last nail in the coffin of the theory of ether. It was known that the laws of mechanics were the same in various coordinate systems, moving uniformly with respect to each other. The magnitude of various physical quantities is of course different in different frames of reference. They are connected by what are called the Galilean transformations. So let us consider two frames of reference, K and K prime, having a common origin at the time t equal to 0, and that the frame of reference K prime is moving with velocity v with respect to the frame of reference K. Then the relations between the mechanical quantities in the two frames are given by the position vector x prime is equal to the position vector x minus the velocity vector v times the time t. So, if the velocity of a particle as measured in the k and the k prime frame of reference is given by the velocity vector u and the velocity vector u prime respectively, then from the above given Galilean transformations, it follows that the velocity vector u prime is equal to the velocity vector u minus the velocity vector v, the well-known relation between the velocities in two moving frames. The Michelson-Morley experiment. Michelson-Morley experiment was one of the experiments that was performed to ensure, or rather to prove, the existence of ether as a medium of propagation for the electromagnetic waves. And this experiment was performed. Setup of this experiment had basically two mirrors which had almost a 99% reflecting surface, which were kept in an orientation which was perpendicular to each other, and there was another beam splitter which was kept in the middle, and this beam splitter was partly silvered, so that part of the electromagnetic wave that was coming from the source was reflected to one of the mirrors, and the other part of the beam of the electromagnetic wave was transmitted into the other mirror. So in this manner, part of the beam was reflected at right angles to go to mirror, let's say we can call that mirror 1, and the other part of the electromagnetic wave was transmitted through this beam splitter which went to the mirror 2. Now what this experiment did was that once these beams went to the mirror, they were reflected back from the mirror, and then they came back to the beam splitter. So the mirror which was along the axis or the direction in which the electromagnetic wave was originally propagating, so that mirror, the reflected wave from that mirror was again reflected back from the beam splitter and went to the detector, while the electromagnetic wave which was reflected from the beam splitter to go up to the mirror 1, that beam, after getting reflected from mirror 1, came back to the beam splitter and then came to the detector, and the thickness of the beam splitter was kept such that the path difference between the two beams which were reflected from these two different mirrors was either 0, half integral multiple of the wavelength, so that the total path difference between these two would be either 0 or integral multiple of the wavelength, and hence when the beams reach the detector, then there should be no phase difference between the two beams. Now if we look at this setup and we see that this entire setup is moving along the direction of the propagation of the electromagnetic wave with a speed v, then we can again use the same formula for the law of addition of velocities. And since it was assumed that this whole setup was because ether was supposed to be the medium in which the electromagnetic waves were propagating, so in this experiment what Michelson and Morley did was that they had a light which fell on this partly silvered mirror which was at 45 degrees, and so that it could split the electromagnetic beam into two parts and then reached back the detector. And what they wanted to do was that since these electromagnetic waves were traveling in ether, so at the detector they wanted to see that what was the path difference or the phase difference that was introduced because of the reflection of the electromagnetic waves from these two mirrors. So using the law of addition of velocities and accordingly putting it for the ray that is in the perpendicular direction, that is the ray which is going to, let's say, the mirror 1, we have that if the distance between the beam splitter and the mirror is capital L, and v was the velocity with which the entire experimental setup was moving along the direction of the propagation of the electromagnetic wave, and t was the time that these waves took to reach the detector, then for the ray in the perpendicular direction we had L square plus velocity, that is v times t by 2 whole square, is equal to c, that is speed of light, times t time by 2 whole square. So basically this formula shows that the total distance traveled by light, that is L along one direction, so the total distance from the beam splitter to the mirror and back to the beam splitter would be, so that is L, and during this time that the light travels this distance L, the entire experimental setup has moved a distance v times t divided by 2, and this whole should be equal to the total distance traveled by light, which if t is the time taken to cover this distance, then the time would be c times t divided by 2. So if we write this, so it becomes a right angle triangle kind of a thing, and the equation can then be written as L square plus v times t divided by 2 whole square is equal to c times t divided by 2 whole square. And from this we can calculate the time that the electromagnetic wave takes to go from the beam splitter to the mirror and back, and that is time t is equal to twice L by under root c square minus v square. Here what is important to note is that the time taken by the electromagnetic wave to go from the beam splitter to the mirror is taken as t by 2. So similarly for the second ray, the electromagnetic wave is propagating along the same direction, goes to the mirror and gets reflected back. So for the onward moving beam, that is the electromagnetic wave which is going from the beam splitter to the mirror, the time of travel is, if L is the distance between the beam splitter and the mirror, then the time of travel is L upon c minus v, where c minus v denotes the relative velocity between the speed of light and the velocity with which the experimental setup is moving along the direction of propagation of the electromagnetic wave. While for the reflected wave from this mirror, the time taken would be L upon c plus v. So the total time t prime taken for this electromagnetic wave to go from the beam splitter to the mirror and back to the beam splitter would be twice L times c upon c square minus v square. And if we compare this formula with the formula that we had obtained above for the ray which went in the perpendicular direction, we see that these two formulae are not equal. Postulates of special theory of relativity. So if we have two mirrors that are rotated through 90 degrees and t prime are interchanged, and this should lead to a shift in the interference pattern. The experiment, however, showed no shift in the interference fringe pattern, implying that the two times are exactly the same. Here t and t prime refer to the two times of travel of the light waves. Alternatively, whereas the laws of mechanics were known to be invariant under Galilean transformations, wave propagation is not. We either have to accept that Galilean transformations apply only to mechanics. For electromagnetic phenomena, there is a preferred frame, the rest frame of ether. However, all attempts to find motion relative to ether failed altogether. None of the attempts to find an explanation within the ether hypothesis was really satisfactory. Postulates of the special theory of relativity. Einstein rejected the very hypothesis of ether, lock, stock, and barrel. He put forward his new postulates of special theory of relativity with revolutionary consequences. Along with the quantum theory, this special theory of relativity turned the physics upside down on its head. Lorentz transformation. Lorentz transformations basically define the transformations in four-dimensional space, which is also called the Minkowski space or the space-time. So here what we do is that normally when we consider a three-dimensional space which has coordinate axis along the x-axis, the y-axis or the z-axis, and then we can do those transformations to other coordinate systems also, like cylindrical coordinate system or spherical polar coordinate system and so on. However, when we talk of special theory of relativity, then we see that we have to add another dimension to our space concept, and that fourth dimension that we have to add is that of time, because relativity also involves time. So when you include this fourth dimension also, then the space or the coordinate system that we get is called the space-time coordinate system or the Minkowski space. So at any point in this space, whenever we have to define a system or an event, then we have to consider all the four coordinates, that is the x, y, z and t coordinate, and that such a point in space is called an event. Now let us look at what these Lorentz transformations do. So basically the Lorentz transformations define the transformation from one coordinate system into another coordinate system of various physical quantities. In particular, Lorentz transformations define the transformation of these coordinates, that is the x, y, z and t coordinates, from one coordinate system into another coordinate system, or one frame of reference into another frame of reference, where these two frames of reference, it is very important to note over here, are both inertial frames of reference. And when I say inertial frames of reference, what I mean is that both these frames of reference that we are considering are non-accelerating frames of reference. The other important thing that we need to understand over here is that these two frames of reference are such that one frame of reference is moving with respect to the other frame of reference with a constant velocity. So there are these two prerequisites that one needs to keep in mind while discussing Lorentz transformations. Number one, that both the frames of reference that we are considering have to be inertial frames of reference or non-accelerating frames of reference. And secondly, that the relative velocity between one frame of reference and the other frame of reference is constant. Now, let us choose one frame of reference and denote it by k, which has coordinates denoted by x, y, z and t. And let us choose another frame of reference which is denoted by k prime, and which has coordinates denoted by x prime, y prime, z prime and t prime. So now the frame k prime, which is moving, let's say, along the positive x direction with a speed v with respect to the frame k, then if we want to do a transformation to the frame of reference which is k prime, that is, we want to do a coordinate transformation, then let us see what are the equations that we need to consider over here. So firstly, what we will see is that if we have light, that is electromagnetic wave, which is moving along, let's say, the x-axis, then in time t, this light wave will cover a distance x is equal to plus minus ct, that is c times t, where c is the velocity of light and t is the time taken or the time of measurement in the k frame of reference. So if we rearrange these terms, then we get x square minus c square times t square is equal to 0. Here if we look at the equation, we will see that the plus minus sign that has been taken for x is equal to plus minus ct. So that plus minus sign basically denotes whether we are moving along the positive x-axis or along the negative x-axis. Now rewriting this same equation for the three-dimensional space, so for the frame of reference k, we can write this as x square minus y square minus z square minus c square t square is equal to 0. And this similar equation can also be written in the k prime frame of reference as x prime square minus y prime square minus z prime square minus c square times t prime square is equal to 0. Here it is important to understand that the primed coordinates refer to the k prime frame of reference, while the normal coordinates refer to the k frame of reference. So if we look at these two equations, what we see is that in both these frames of reference, that is in the K frame of reference and K prime frame of reference, these equations come out to be the same. So we can then establish a kind of an equality between these equations that we've obtained in these two different frames of reference for the coordinates as x square minus y square minus z square minus c square times t square is equal to lambda times bracket open x prime square minus y prime square minus z prime square minus c square times t prime square. And now, since where lambda is a constant, or which basically relates the two equations that we've discussed above in the two frames of reference. And since this relation must hold also for inverse transformation as well, therefore we see that lambda square is equal to 1. This we will get if we substitute the value of x prime square minus y prime square minus z prime square minus c square t prime square in this equation in terms of the x square minus y square minus z square minus c square t square. So then we'll get a lambda into lambda, that is lambda square, and this should again, the final equation that we will get will again have the components x square minus y square minus z square is equal to c square times t square is equal to lambda square bracket open x square minus y square minus z square minus c square times t square bracket close. So since the coordinate terms on both these sides of the equation cancel out, so we'll have lambda square is equal to 1 or lambda is equal to plus minus 1. And from the identity transformation, one can conclude that lambda has the value 1. Lorentz transformations. So from the above equations, one can then finally conclude, taking the value of lambda is equal to 1, that x square minus y square minus z square minus c square times t square is equal to x prime square minus y prime square minus z prime square minus c square times t prime square. Now here one basic assumption that we have made, or rather what we have also shown from these above equations, is that under Lorentz transformations, the condition that has to be satisfied is that they are a set of linear transformations under which the term x square minus y square minus z square minus c square times t square remains invariant. And this is something that we have already seen when we did this transformation in going from the frame of reference K to the frame of reference K prime. We saw that the equation in both these frames of reference comes out to be equal, and therefore we can say that this is invariant under transformation, under linear transformation of the coordinate system. And such transformations which remain invariant in going from one frame of reference to another frame of reference, such equations are called Lorentz invariant equations. So now let us just consider one dimension in the space, in this 4-dimensional space. That is, let us consider only along the x-axis. Then the above equation can then be reduced to x square minus c square times t square is equal to x prime square minus c square times t prime square. Here another important point that we need to note is that while going from one frame of reference to the other frame of reference, we have taken the transformation of, let's say, the x-axis going from x to x prime, the y-axis going from y to y prime, and the z-coordinate going from z to z prime, and the t, that is the time coordinate, going from t to t prime. However, the speed of light c is again invariant under such transformations. So that is another important thing that you need to keep in mind. Now, this equation that we have just seen is like a rotation but with a sign difference. So in order to do a transformation, let us first define a set of transformations that can take the coordinates from one frame of reference to the other frame of reference. So in order to do that, let us write down x prime as being equal to cos hyperbolic of theta whole times x plus sine hyperbolic of theta whole times c times t. Similarly, For the time coordinate, we can write down c times t prime is equal to sine hyperbolic of theta whole times x plus cos hyperbolic of theta whole times c times t. Now let us look at the origin of the frame of reference k prime. So at the origin, the coordinate x prime is equal to 0, while in terms of the frame of reference k, the origin of the frame of reference k prime is at a distance x is equal to vt, or v times t, where v is the speed or the velocity with which the frame k prime is moving along the positive x-axis with respect to the frame k. Hence, from these two above equations, we can write down, so tan hyperbolic of theta is equal to minus v by c, and cos hyperbolic of theta is equal to 1 upon under root of 1 minus v square by c square. These two equations we get when we put x prime is equal to 0 and x is equal to vt in the above two transformation equations that we had defined for x prime and c times t prime. And finally, from the equations of tan hyperbolic and cos hyperbolic, then we can write down the equation for sine hyperbolic, which is given as sine hyperbolic of theta is equal to minus of v by c whole times upon under root of 1 minus v square by c square. Now, if we define beta is equal to v by c and gamma is equal to 1 upon under root 1 minus v square by c square, which is equal to 1 upon under root 1 minus beta square, then the equations for x prime and c times t prime can be written as x prime is equal to gamma times bracket open x minus beta times c times t bracket close, and c times t prime is equal to gamma times bracket open minus beta times x plus c times t bracket close. Lorentz transformations. So these equations that we have defined for x prime and c times t prime are called the Lorentz transformation between two inertial frames of reference. And just like we have defined these Lorentz transformations in going from the frame of reference k to the frame of reference k prime, in a similar manner, we can also define the inverse transformations in going from the frame of reference k prime to the frame of reference k. And when we do that, what we have to basically do is that the transformations that we defined for x prime and c times t prime are now to be defined for x and c times t, and these will be defined in terms of the coordinates x prime and c times t prime. Further, if we have to look at the frame of reference k with respect to the frame of reference k prime, then what we see is that the frame of reference k is moving with a speed minus v with respect to the frame of reference k prime along the negative x-axis. So doing these transformations, we can obtain the Lorentz transformations for the coordinates x and c times t in the frame of reference k with respect to the coordinates x prime and c times t prime in the frame of reference k prime as x is equal to gamma times bracket open x prime plus beta times c times t prime bracket close, and c times t is equal to gamma times bracket open beta times x prime plus c times t prime bracket close. So in the four-dimensional space, this special Lorentz transformation in which the relative motion of the two frames of reference is along the x-axis can then be written as, so here the equations that we are going to write down are basically the equations of these coordinate transformations from one frame of reference, that is k, to the other frame of reference k prime. And then we will also be writing down the equations for the coordinate transformations from the frame of reference k prime to the frame of reference k. So when we go from the frame of reference k to the frame of reference k prime, they are called the Lorentz transformations of the coordinate system. And when we go from the frame of reference k prime to the frame of reference k, then they are called the inverse Lorentz transformation of the coordinate system. So the Lorentz transformations can be defined as x prime is equal to gamma times bracket open x minus v times t bracket close, t prime is equal to gamma times bracket open minus v by c square times x plus t bracket close, y prime is equal to y, and z prime is equal to z. Here it is important to note that this y prime is equal to y and z prime is equal to z will only be valid when the frames of reference are moving with respect to each other. That is, let's say the frame of reference k prime is moving with respect to the frame of reference k along the x-axis only. There is no relative motion between these two frames of reference along any other coordinate direction. Similarly, the inverse Lorentz transformation can then be defined as x is equal to gamma times bracket open x prime plus v times t prime bracket close, t is equal to gamma times v by c square times x prime plus t prime bracket close, y is equal to y prime, and z is equal to z prime. So here again what we see is that the transverse coordinates, that is the coordinates y and z in the k frame of reference and y prime and z prime in the k prime frame of reference, remain unchanged so long as the relative motion between the two frames of reference is only and only along the x-axis. Now, in case of the relative velocity v of the two frames of reference being along a general direction, the resultant Lorentz transformation equations are then given by t prime is equal to gamma times bracket open t minus velocity v dot product or scalar product with coordinate x upon c square is equal to gamma times bracket open t minus vector beta dot product with vector x by c bracket close, x prime vector is equal to x vector plus gamma minus 1 by v square times dot product of vector v with vector x times vector v minus gamma times vector v times time t, and this is equal to vector x plus gamma minus 1 by beta square times within brackets vector b beta dot product with vector x bracket close times vector beta minus gamma times vector beta times time t upon c. And we can then further write this as t prime is equal to gamma times bracket open t minus within brackets vector beta dot product with vector x bracket close upon c whole bracket close, vector x prime parallel, that is along the direction of the relative motion, is equal to gamma times bracket open vector x parallel minus beta times c times t bracket close, and vector x prime perpendicular is equal to vector x perpendicular. Here vector x parallel and vector x prime parallel are the components of the coordinate along the direction of the relative motion between the two frames of reference, while the vector x perpendicular and the vector x prime perpendicular are the coordinates along the two transverse directions with respect to the direction of the relative motion between the two frames of reference. O vectors. Now, as we have already been discussing in the Lorentz transformations, that when we have to take into account the special theory of relativity, then we cannot just consider the three-dimensional space, that is the x-axis, the y-axis and the z-axis, but we have to instead consider the four-dimensional space, which also includes the coordinate of time, that is t, x, y and z. So, or in order to make a formulation where we can consider this four coordinate space, we introduce the concept of four vectors, where the coordinates t, x, y and z are denoted by x superscript 0, x superscript 1, x superscript 2, and x superscript 3 respectively. Here, if we try and compare the space-time coordinates with this new coordinate system that we have just introduced, then x superscript 0 is equal to c times t, x superscript 1 is equal to x superscript 2 is equal to y, and x superscript 3 is equal to z. And in this new notation, the Lorentz transformations can then be rewritten as x superscript 0 prime is equal to gamma times bracket open minus beta times x superscript 1 plus x superscript 0 bracket close. X superscript 1 prime is equal to gamma times bracket open x superscript 1 minus beta times x superscript 0 bracket close. X superscript 2 prime is equal to x superscript 2, and x superscript 3 prime is equal to x superscript 3. Here we use the Greek symbols for the space-time coordinates and the Latin symbols for space coordinates. So x subscript I is equal to, or rather equivalent to, x subscript 1, x subscript 2, x subscript 3, while x superscript mu is equal to x subscript 0 and the x vector. So basically here what we see is that x superscript mu will have mu running from 0, or rather have mu taking the values 0, 1, 2 and 3. So x superscript 0 is equivalent to x subscript 0 or c times t, and the x superscript 1, x superscript 2 and x superscript 3 denote the position vector x. And according to this notation that we have just described, we can expect that many physical quantities transform under Lorentz transformations, like the space and time coordinates of a point. So by analogy with ordinary vectors, we can speak of four vectors. So basically, just like ordinary vectors have three components along the x, y and z direction, similarly in case of this new formulation that we have considered, which we define or denote as the four vectors, here we will have the four vectors as having four coordinates: x superscript 0, x superscript 1, x superscript 2 and x superscript 3, where x superscript 0 is the time coordinate and the remaining three are the space coordinates, and these taken together are called the four vector coordinate representation. Length, contraction and time dilation. Now let us try and look at some of the effects that this Lorentz transformation has on the measurements that are done in the two different frames of reference. So here what is important to understand is that the event or the measurement that is being done for the same event, however, the measurement is being done in two different frames of reference, which are both inertial frames of reference, but are moving relative to each other with a speed v. So just like the case that we discussed when we wanted to define our Lorentz transformation, we taking a similar case where we will have, let's say, two frames of reference given by k and k prime, such that the k prime frame of reference is moving with respect to the k frame of reference with a speed v along the positive x direction, and satisfies the Lorentz transformations given by x prime is equal to gamma times bracket open x minus v times t bracket close, t prime is equal to gamma times bracket open minus v by c square times x plus t bracket close, or the inverse Lorentz transformations, which are given by x is equal to gamma times bracket open x prime plus v times t prime bracket close, and t is equal to gamma times bracket open v by c square whole times x prime plus t prime bracket close. So now if we consider two events that are simultaneous in the frame of reference K, that is events defined by x1, t1 and x2, t2 are simultaneous such that t1 is equal to t2 are not simultaneous in the frame of reference K prime. And the reason for this is that if we do a Lorentz transformation of t1 to t1 prime, then we have, and t2 to t2 prime, then we have t1 prime minus t2 prime is equal to gamma times bracket open minus v by c square bracket close whole times bracket open x1 minus x2 bracket close, and this is not equal to 0 for x1 not equal to x2. Hence, simultaneity is no longer a universal concept, but under the Lorentz transformations or in the special theory of relativity, it becomes a relative concept. In the Newtonian mechanics, time flows at the same rate in all frames of reference. Therefore, there we can talk of simultaneity of events in different frames of reference as being universal, but that same thing does not hold true when we consider the principles of special theory of relativity and consider Lorentz transformations instead of Galilean transformations. So one of the basic measurements or the basic experiments that we do is to measure the length of a rod in the two frames of reference, that is in the K frame of reference and in the K prime frame of reference, and see that what is the effect that these measurements will have in these two different frames of reference. So let us consider the length of the rod as being L prime lying across the x prime coordinate axis in the K prime frame of reference. Now the coordinates of the rod in the K frame of reference are given by x1 t1, that is the initial point, and x2 t2, that is the final point. In the K prime frame of reference, these two ends of the rod are defined by the coordinates x1 prime, t1 prime for the initial end, and x2 prime and t2 prime for the farther end or the other end. Now, if we define the length of a moving rod to be the distance obtained by measuring the positions of the two ends of the rod simultaneously, that is t1 is equal to t2, then the length of the rod in the frame of reference in which the rod is stationary is given by L prime is equal to x2 prime minus x1 prime is equal to gamma times bracket open x2 minus x1. So here we have done a Lorentz transformation in going from the frame of reference K prime, which is moving with the rod, to the frame of reference K in which the rod appears to be moving, and the frame of reference K prime also is moving along with the rod. So in other words, what one is wanting to say is that in the K prime frame of reference, the rod is stationary. So L prime is equal to gamma times L, follows that L is equal to L prime by gamma. That if we calculate the length of the rod which is moving with respect to that frame of reference with a speed v along the positive x-axis, then the length of the rod appears to be shorter as compared to its length when measured in a rest frame of reference, that is a frame of reference in which the rod is at rest. Length, contraction, and time dilation. So, like we were discussing just now, that the length of the rod appears to be contracted in the moving frame of reference, that is in the K frame of reference, by a factor gamma, where gamma was equal to 1 upon under root 1 minus v square by c square. And what is very important to note over here is that the speeds at which we deal with in our daily life, that is the speed with which probably we are moving or the speeds with which our vehicles are moving, If we compare those speeds with the speed of light, then these speeds are negligible in comparison with the speeds of light. Hence, this length contraction is something that we do not normally observe in our daily life, and hence does not seem to hamper with our normal measurements that we do taking the help of Galilean transformation and Newtonian mechanics. However, if the speed of motion of this rod, or for that matter any other object, is close to the speed of light, that is, when we say that v is close to c, then the term gamma becomes very large, because v by c comes close to 1. So gamma, which is equal to 1 upon under root of 1 minus v square by c square. So the term in the denominator becomes almost close to 0 or approaches 0. Hence, gamma approaches infinity. And for such cases, the length contraction becomes very significant. Now, if we use the inverse transformation, it is easy to see that the rod is stationary in the K frame of reference, will then appear to be contracted in the K prime frame of reference by the same factor, gamma. Now let us consider the space-time coordinate systems of a clock to be x1, t1 and x2, t2 in the K frame of reference. So these same coordinates in the K prime frame of reference would be given by x1 prime, t1 prime and x2 prime, t2 prime. Now, if the clock is at rest in the K prime frame of reference, then x1 prime is equal to x2 prime. However, if we use the inverse Lorentz transformations, then t2 minus t1 in the K frame of reference is equal to gamma times bracket open t2 prime minus t1 prime bracket close, or delta t, which is equal to t2 minus t1 is equal to gamma times delta t prime, where delta t prime is equal to t2 prime minus t1 prime. Here delta t is the interval between two events in the moving frame, and delta t prime is the interval or the time interval between the same two events in the rest frame of reference, that is the frame of reference in which the events are at rest. Thus, from the above equation that we see for the time interval between two events in the moving frame, we see that the time is dilated or expands in comparison to the time measurement done for the same two events in the rest frame of reference. So, just like length contracts in the moving frame of reference, similarly time dilates in the moving frame of reference, and this phenomena of dilation of time in the moving frame of reference is called time dilation. The relativistic Doppler shift. We have already seen, or we already know about the Doppler shift, which basically refers to the change in the frequency of sound waves when approaching or moving away from a source or the observer. The same Doppler shift or Doppler effect is also observed in case of light or the electromagnetic waves. However, in this case, we need to consider the relativistic effects due to the special theory of relativity. Also, in order to accurately find out that what is the Doppler shift or the shift in the frequencies when these measurements are done from two different frames of reference which are in relative motion with each other, or when the light source and the observer are moving towards each other or moving away from each other. So, the first thing that we need to understand over here is that the relativistic Doppler effect is different from the non-relativistic Doppler effect. Second important fact that we need to take into consideration over here is the time dilation of the special theory of relativity. And the third important aspect that we need to take into consideration is that it does not involve the medium of propagation as a reference point. So, again, taking two frames of reference that is the k frame of reference and k prime frame of reference, which are both inertial and moving relative to each other, and also taking then the Lorentz transformations are given by x is equal to gamma times x prime plus v times t prime bracket close, and t is equal to gamma times bracket open v by c square times x prime plus t prime bracket close, y is equal to y prime, and z is equal to z prime. So from these Lorentz transformations, we can then write down the formulae or the relation for the speed, which is given as derivative of x with respect to time, that is dx by dt, is equal to bracket open derivative of x prime with respect to time t prime, that is dx prime by dt prime, plus v bracket close whole upon bracket open 1 plus v by c square whole times derivative of x prime with respect to t prime, that is dx prime by dt prime bracket close. So a signal source which is placed at the origin and is stationary in one frame of reference, and let us consider another frame of reference which is moving with a speed v along the x-axis or the x prime axis, having its origin O prime, then the source produces two signals at time t1 prime, which is equal to 0, and time t2 prime, which is equal to 1 upon f prime. So if we want to, so basically what we are wanting to do is that at the initial time t1, both the frames of reference are coincident, that is their origins coincide, and then at that subsequent time t2, the two frames of reference are no longer coincident and the k prime frame of reference has moved with respect to the k frame of reference. So the time measurement in the k prime frame of reference would be t1 prime and t2 prime, while the time measurement in the k frame of reference would be t1 and t2. So if we want to define the coordinates of the two events, that is the signal source emitting two signals at these two different points in time, then these coordinates in the k prime frame of reference are given by, where 0, 0 refer to the time 0 and the coordinate position 0, and 0 and 1 upon f prime refers to the coordinates after at the later time t2 prime. Similarly, in the k frame of reference, these coordinates appear to be 0, 0 and gamma times v by f prime and gamma by f prime. So here we have done Lorentz transformation to get the coordinates in the k frame of reference. The relativistic Doppler shift. So the period between the pulse in the k frame of reference between these two events is t2 minus t1 plus the time taken by the pulse to travel from x2 to x1. Now the speed of the pulse towards observer in the k frame of reference is minus u prime, if we are assuming that the frame of reference k prime was moving with respect to the frame of reference k. Then in the k frame of reference, the speed of the pulse is given by minus u is equal to minus u prime plus v upon 1 plus within brackets minus u prime times v by c square. So here what is important to note is that u is the speed of the pulse in the k frame of reference and u prime is the speed of the pulse in the k prime frame of reference, while v is the speed of the frame k prime moving along the positive x-axis with respect to the frame of reference k, and c is the speed of light. So the time period between the two pulses in the k frame of reference, which is denoted by tau, is equal to t2 minus t1 plus bracket open gamma times v by f prime bracket close whole times bracket open u prime minus v upon 1 minus u prime v by c square bracket close whole inverse. And this is, if we simplify this further, we get tau is equal to gamma by f prime plus gamma by f prime whole times v by u prime minus v whole times bracket open 1 minus v times u prime by c square bracket close, or the frequency of the pulses f as given by f is equal to 1 upon tau is equal to gamma times bracket open 1 minus v by u prime bracket close whole times f prime. Now if v is much less than c, then it implies that c almost tends to infinity and gamma tends to 1, and this leads to the classical Doppler formula of the frequency f being equal to bracket open 1 minus v by u prime bracket close times f prime. For electromagnetic radiation, u prime is equal to c, and therefore the Doppler formula from the above relation is given by f is equal to f prime times under root of 1 minus beta upon 1 plus beta, where beta is v by c, and follows that lambda, that is the wavelength of the pulse, is given as lambda is equal to lambda prime times under root of 1 plus beta upon 1 minus beta. Here lambda prime is the wavelength of the pulse in the k prime frame of reference, and lambda is the wavelength of the pulse in the k frame of reference. So in the limit of the Newtonian mechanics where c tends to infinity and beta tends to 0, the frequency f is equal to the frequency f prime. And this is the correct result in the Newtonian mechanics, but obviously in disagreement with the experiment that we are performing over here to study the relativistic Doppler shift. So students, let us summarize what all we have learned in this module. Firstly, we learned about the situation that the physics was facing at the end of the 19th century. The crisis faced by physics due to the problem of velocity of light was explained. Then, a major development was the Michelson-Morley experiment, which described that the null result of this experiment showed that ether does not exist, and this experiment led to a paradoxical situation wherein on the one hand people were thinking that ether was the medium in which the light rays propagated, but the null result of this experiment proved counterwise. That is, it proved that there was no such medium as ether. So this led to a very peculiar and paradoxical situation for the physicists of those times, and that situation was resolved by Einstein in his theory of relativity, that is the special theory of relativity. So the postulates of the special theory of relativity were then described in this module, and discussing these postulates, one can then lead to a complete paradigm shift in the description of the space-time coordinates. That is, for the first time, this theory took into account not just the three space coordinates, but also the time coordinate. Having taken all of these coordinates into account, that is the space-time coordinates into account, we then discussed the Lorentz transformations, which defined the coordinates of events as viewed in the moving frames of reference, which replaced the Galilean transformation of the Newtonian relativity, and showed conclusively that the Lorentz transformations are the real transformations when one moves from one frame of reference to the other frame of reference, and that Galilean transformations are a mere approximation but are incorrect. We then discussed the revolutionary and the counterintuitive implications of the consequences of the Lorentz transformations. That is, we saw what effect this motion, relative motion between the different frames of reference had on the length measurements and on the time measurements of events, and these were termed or described as the length contraction and the time dilation. Finally, we discussed the relativistic Doppler effect and showed that this is different from the normal Doppler effect that we have known up till now. Thank you.